Hello students, Professor Nugent here. In this video, we are going to discuss how to search for a break, a change in the estimated coefficients in your autoregressive model when you don't know the break date. Say you might suspect that there is a break, but you don't know exactly when that break is. You might want to test the null hypothesis of coefficient stability against some general alternative that there has been a break sometime, or multiple breaks, or perhaps some general evolution, a slow change in the coefficients over time. Even if you think you know the break date, if that knowledge is based on prior inspection of the series, then you have in effect estimated the break date, and this invalidates the Ch test critical values. Now, why is that? Well, if you have estimated the break date, then the break date is a random value, and there are a range of possible break dates which give you many possibilities of rejecting the null hypothesis. And this means that, well, we need higher critical values in that case. That's the case that we're going to look at, but in a more structured way. So let's look at the quant likelihood ratio statistic, also called the sup-walled or supremum walled statistic. Supremum is like maximum of the walled statistic. The QLR statistic is the maximum Ch statistic. Ch walled, we're talking about F statistics here. Let F equal the Ch statistic, testing the hypothesis of no break date at date tau. The QLR statistic is the maximum of all of the Ch F statistics over a range of tau between tau naught and tau 1. And that's given by this expression here. You will have a series of F statistics, F of tau naught plus 1, all the way through F of tau 1 minus 1, all the way to F of tau 1. A conventional choice for tau naught and tau 1 are the inner 70% of the sample, exclude the last 15%. Now, should we use the usual F critical values? We have just discussed that when there is a range of possible break dates, then there is a multiple possibilities of rejecting the hypothesis of no break. And so what happens is that in effect there's greater uncertainty. So we need larger critical values. The large sample no distribution of f of tau for a given fixed, not estimated tau, is f of q infinity. All right, that's our usual F distribution that we would draw critical values for the Ch test with a fixed, not estimated given break date. But if you get to compute two Ch tests and choose the biggest one, the critical value must be larger than the critical value for a single Ch test. You have greater uncertainty there. If you compute very many Ch statistics, for example, all dates in the central 70% of the sample, the critical value must be even larger because you have even more uncertainty. So we need an even larger test statistic. So in large samples, QLR has this distribution. All right, so this is the 1 over q times the sum from I equals 1 to q of bi of s squared over s times 1 minus s, where bi for I equals 1 through n are independent, continuous time Brownian bridges on 0 for s between 0 and 1. A Brownian bridge is a Brownian motion deviated from its mean. A Brownian motion, this is a Gaussian normally distributed random walk in continuous time where a equals 0.5 because you have excluded the first and last 15% of the sample. The critical values of this thing are tabulated in Stockham-Watson table 14.5. And if you run this test in Stata, as we have discussed in this Stata tutorial, the critical values will be produced for you. Here is the table. The critical values for the QLR statistic with 15% trimming with the number of restrictions Q. Alright, so we're looking at the number of restrictions Q, and you can see with 15% trimming, at 5% with one restriction, you have an 8.68 critical value. So this is a larger critical value than the F, the typical F critical value. And the table continues for even more restrictions. And if you have a large number of lags in your ADL model, you're going to have many restrictions. Let's look at an example. Has the GDP term spread relationship been stable over time? We're going to look at, we'll call that this is an ADL, autoregressive distributed lag model with 2 lags of the y variable, 2 lags of the x variable. The y variable is the GDP growth rate, the x variable is the term spread. We're estimating this model over 1962 quarter 1 through 2017 quarter 3. The estimated regression is a prediction of the GDP growth rate equal to 0.94 plus 0.25 times the lag of the GDP growth rate, first lag, plus 0.18 times the second lag of the GDP growth rate, minus 0.13 times the first lag of the term spread, plus 0.62 times the second lag of the term spread. So we're asking, has this model been stable over the full period of 1962 through 2017? In other words, a way to think about this is if you chopped up the period in half and you estimated this regression twice. You estimated the regression for the first half of the series and the second half of the series, would you get the same coefficients for the first half of the series as you did for the second half of the series? That is a rough idea of what we're asking. Or have the coefficients changed over time? So our dependent variable, that's our GDP growth rate, the regressors is the intercept, the first lag of the GDP growth rate, second lag of the GDP growth rate, the first lag of time spread, and the second lag of time spread. We are testing for a constancy of intercept and coefficients on the first and second lag of term spread, the coefficients on the first and second lag of GDP growth rate are constant. The QLR test statistic with 3 coefficients, because we're testing intercept and coefficients on term spread t-1, term spread t-2, is 6.47, which is greater than the 1% critical value for 3 restrictions, so we reject the null hypothesis that there is no break for the alternative that there is a break date. And the estimated break date is 1980, quarter 4. So we estimate a break date of 1980, quarter 4. So the relationship between term spread and GDP growth rate changes after 1980, quarter 4. Let's look at a plot of this. The F statistics, here we have the F statistics testing for a break date in equation 15. So this is our equation 14.15 at different dates. And what QLR is doing is looking for the largest F statistic. These are all of the F statistics testing for the break dates at all of these periods. So we're going to test for a break date at every single year. Okay, between the 15%, we have a 15% trim on this side, we have a 15% trim on this side, and we're going to test whether there is a break date at all of the years in between. And this plot shows the F statistics testing a break date here, a break date here, a break date here, so on and so forth. And what QLR is doing is looking for the largest F statistic. The largest F statistic is the QLR statistic, which is 6.47. It's right here. And that is where we get our 1980 Q4 break date.